Hi, welcome back to CEE222 week 14 recitation. So that started with the first problem, problem 11.3.5. So in this problem, we want to determine the roundoff depth and also the volume of the roundoff of given locations at the Miami, Florida, and with the 10-year 24-hour storm. And the problem also tells us the soil in the region is sand and gravel. So that's actually tells us we should use the soil group A because sand and gravel have a coarse pores, so the water can easily infiltrate into the ground, and we categorize that as the soil group A. Okay, so in order to apply the SCS runoff curve, we need to calculate the eigenvalue first. And the problem tells us that we have 25 acres of commercial development and 75 acres of townhouse. So we can use this as the weight to calculate the average curve number for this region. So let's do that. So we already know that the soil group is A. So we can use the table 11.7 to find out the corresponding curve number for the commercial area, which is this one. So it's 89, and the other one is the townhouse development, which is this one. So it's 77. Okay. Then we want to calculate the area weighted average for the representative CN number for this region, for this watershed. So we can say that the CN number of this region, of this watershed, equal to the area 1 times CN number 1 plus area 2 plus CN number 2 and divide by the total area, which is area 1 plus area 2. And we plug in a number. So the area for the commercial development is 25 acres. So let's write down 25 acres. And the CN number of this region, the commercial development, is 89. So times 89. And we know the townhouse area is 75. If you forgot, I show you again here, 75. And the CN number is 77. And divide by the total area, which is 25 plus 75. So with this equation, we can get that CN number, the area weighted CN number is 80. So next step, we can use the equation of the SCS curve method to calculate the roundoff. Okay. So let's use the equation 11.6, where the soil moisture storage deficit in each at the time of runoff begins. This ACE is equal to 1000 minus 10 times Cn divided by Cn value. So this tells us the ACE. You plug the 80 into this CN number, you can get the ACE is 2.5 inches. Then we can apply the equation 11.5 to calculate the roundoff R, that is equal to the precipitation minus 0.2 of the ACE, the soil moisture storage deficit, to the power of 2 divided by K plus 0.8 ACE. Okay, so we want to identify the rainfall amount, this p-value, and this p-value is 10. It's designed for the 10-year 24-hour storm, and it's happening in Miami. So we can use this following figure 11.5, which is the contour map for the 10-year 24-hour rainfall in the US. In Miami is around here. So we use 9-inch rainfall to represent this 10-year 24-hour rainfall. So with that being said, the P is equal to 9-inch in this case. So we plug in the ACE, this 2.5 to this equation, also this p-value 9-inch to this equation, we can calculate that the runoff depth is equal to 6.57 inches. And the problem also asks us to calculate the volume of the runoff. So to convert the depth to the volume, we need to further times the area of this region. So let me write down here, runoff volume is equal to 6.57, and we convert inch to feet, which we divide by 12, and times the acre, times the area in the unit of acre, and that is 100, because 25 plus 75 is equal to 100. So we can guess that the total runoff volume is 54.8 acre feet. Okay, so basically we just need to utilize the table 11.7 to identify the corresponding curve number for the region, and use the contour map figure 11.5 to identify the rainfall amount for the 10-year 24-hour storm in Miami. Then we can apply the SCS curve number method to calculate the runoff, and you can easily convert the runoff depth to the runoff volume by timing the total area. Okay, so that's straightforward. We can move on to the next question. Okay, in this problem 11.3.7, we will follow the same procedure as the previous problem. But in this case, we have more diverse land cover in this region. So we have 20 hectares of the golf course and 30 hectares of commercial area and 50 acres of residential area with different soil type. And we already know that the p-value, the rainfall value, is equal to 15 centimeter, which is equal to 150 millimeter. Okay, so the only thing, and the problem also asks us to calculate the runoff volume. So we can use the SCS curve number method to calculate the roundoff depth and convert to the roundoff value as we did before. And so the first step is to identify the area weighted curve number for this region, so we can apply the equation. Okay, so let's start with that. So let's first identify the soil group for this different soil type. This Trixo soil, according to this description, is coarse to fine texture. So this is B soil, because it's coarse to fine, is not coarse, but it's in the next level. So A will be the coarse. Okay, and B is coarse to fine, and C is finer soil, and the D is the most finest soil. Okay, so the primer are moderately fine to fine texture. So this would be C category, C group for the soil type. And for the Donica or sandy soil, so sandy is water can easily infiltrate into the sand. So use that concept, we categorize it as the group A. Okay? And for the first type, for the first fraction of the land cover is the golf course. So let's try to find the corresponding cover description. So the golf course can be viewed as the open space and is in a good condition because it's mainly covered by grass. Okay, and it tells us we have 40% in Trixo soil and rest of the dam, and the rest in the primer soil. So that means we need to use the value for Trixo is in category B group. So this value it's not the poor condition. It's a fair condition. It's because the golf course is mainly in the grass, right? So let's phrase this. So we will need this 16.1 value for the primer part. Oh no, for Trixo part. For this will be 61, and the primer soil is category is group C. So we need this 74. Okay, and for the next next land cover is the commercial area. So it will be this one, and it has the primer soil that is group C. So it's 94. Okay, so let's also write this down, 94. Okay, and next one is the residential area. and is townhouse, right? No. What do we have here? Is 1.5 acre of lot and is in Conductivity soil is group A, so it's 54. Okay, so we also identified this one is 54. Okay, then I will just use those values to write the area weighted CN number equation for you. You just need to times the corresponding area, then you can do that, and I will leave that to you. The CN value will be 8 times 61 plus 12 times 74 plus 30 times 94 plus 50 times 54. So this is the first two terms is for the golf course, and because golf course we need to further separate into these two soil type, soil group. So we have two terms for that, and you just need to divide by the total area, which is 100 hectare in this case. Then we can get the CN number for this region is equal to 69. After we get this, we can apply the equation 11.7, 11.5 to calculate the roundoff. So similarly, we need to first calculate the A's value and the equation you can copy from here, similar to this one, but this time we will use different unit. So it's 25,400 minus 254 times the CN value that we calculate is 69, divide by the CN value 69. So we'll get 114 millimeter. And then we can apply this equation 11.5 to calculate the roundoff depth. And the P value is equal to 150 millimeter. So we can just put that value into our equation. It's 150 minus 0.2 times the A's value, 114, and the entire term to the power of 2, divide by 150, the P, plus 0.8 times the A's value, 114. So we can get that the roundoff depth is 67.1 millimeter. So the total roundoff volume is 0.0671 meter. We just convert this unit, this depth unit, to meter, times 100 hectare. And we also need to convert this to the square meter, which is 10,000. 1 hectare is equal to 10,000 square meter. So we can get the roundoff volume is 67,100 cubic meter. Okay, so basically this problem uses exactly same procedure as the previous one, but with more combination to calculate with more complex land cover and soil group. So we just need to identify all those things using the table 11.7 and calculate the area averaged curve number for this region. Okay, let's move on to next one. 11.4.1. So in this problem, we need to determine the time of concentration for the runoff from the concrete parking lot. Okay, so according to the description, we will first have an overland flow segment that is like they need to have this sheet flow to pass this parking lot, and we have the information that the flow segment is 25 meters long with the slope 0.5. So let me just write that down. We have the segment equal to 25 meter, and with the slope at this part is equal to 0.5%. And then the overland flow segment will move water into the shallow V-shaped channel. So we move into a V-shaped channel where we will drop 2 meters in elevation, and over the total length is equal to 100 meters. After that, the stormwater is picked up in a 400 meter long, 2 meter wide rectangle channel. Okay, so we then pass to a rectangle channel that is 400 meter long with the width of the channel is equal to 2 meters. And the flow in this channel is 0.5 meter deep. And the slope for this concrete, this is a concrete channel, the slope is equal to 1%. Okay, and we are calculating the 2-year 24-hour rainfall depth, that is 4 cm. No, you just remember that first. Okay, so that's calculates the total time of concentration first. Then after that, we can calculate the percent of the time of concentration that is attributed by the overland flow. Okay, so for the overland flow, this part is essentially a sheet flow. So that means we can use the equation 11.12, which I already put it here, to calculate the time of concentration. So let me write that down. The segment 1 is 0.091 times n is a concrete parking lot. So the Manning coefficient n is equal to 0.091 0.11. The length is 25 because the segment is 25 meter. Okay, and to the power of 0.8. Then we will divide by the P to the rainfall. Rainfall is 4 cm. Okay. That's weird. Why can the okay. Divide by this is equal to 40 millimeter. Okay, so 40 to the power of 0.5 times the slope is 0.5%, that is 0.005 to the power of 0.24. Okay, then we can calculate that this is 0.043 hours. Okay, and for the second part, this is the V-shaped channel. And this is the shallow concentrated flow. So we will use this equation to calculate the velocity. So V equal to 6.19 times the slope, that is 0.2. 2 divided by 100 is the slope to the power of 0.5. Then we can get the velocity is 2.77 meter per second. Then we can calculate the concentration time, which is equal to the length divided by the velocity, that is 100 divided by 2.77. This will equal to and let's do one more conversion, because this calculate is a second, right? But we want to use the unit in hours, so that is divide by 3,600 over 1 over 3,600 to convert to hours, and this will give us the number 0.01 hours. Okay, and for the last piece, we will use the Manning equation. So the Manning equation, the velocity is equal to 1 over n times hydraulic radius to the power of 2 over 3 times the slope to the power of 1 over 2. So we can plug in a number, and because this is a concrete channel, so the Manning coefficient in this case is 0.013. Times the hydraulic radius, which is this RH is A divided by the perimeter of the weighted perimeter. Okay, so this gives us the area is 2 times 0.5 divided by P, which is 3 meter. That is 0.5 plus 2 plus 0.5, so it's equal to 3. So we got this RH 0.333 meter. We plug that back to this equation, and times the slope is 1%. So it's 0.01 to the power of 1/2. And we get the velocity in this rectangular channel is 3.69 meter per second. So velocimetric, the time of concentration at this segment is the total length divided by the velocity. That is 400 divided by 3.69, and we have this term for the unit conversion to the hours, and we can get that this part is 0.03 hours. So the total time is 0.043 plus 0.01 plus 0.03, which is 0.083 hours. And to find the percentage of the overland flow, we have 0.043. This is the overland flow part, divided by the total time of concentration. This gives us 0.52, which is equal to 52%. Okay. Okay, let's go to the next problem, problem 11.4.2. So similarly, we want to calculate the concentration of time of concentration. And according to the problem description, the flow will first travel over the land surface, so which is the overland flow. Okay, and the elevation change is 3 feet with the length equal to 150 feet. After that, it will move into the shallow concentrated flow. Okay, and in this area we will pass the length 450 feet with a velocity equal to 2 feet per second. And in the last segment, we will pass through a pipe, and it's half full, so it's basically can be viewed as the open channel. And the diameter is 2 feet with the slope equal to 1%. Okay, So let's first calculate the time of concentration on this overland flow, and we will use equation 11.8. The T1 is equal to 0.007 times the main equation. This n value is is for the short grass, so that is this n is 0.15. Okay, and the rainfall is 3.4 inch, so this P is 3.4 inch. So we rewrite this equation down here. So this would be times 0.15 times the length is 150 feet to the power of 0.8 divided by 3.4 to the power of 0.5 times 0.02 to the power of 0.4, and this will give us 0.219 hours. For the second part, we already know the velocity, so it's quite straightforward. That the t for this segment 2 is the length 450 divided by the velocity, and we can get the time, right? And we want to convert this to hours, so we times 1 over 3,600. Then we can get this would be 0.0363 hours. And for the last part, we will use the main equation to calculate the time of concentration of this pipe. So we need to start with the velocity. We use the main equation for the English unit, which is 1.49 divided by the main coefficient, and this is a concrete pipe. So the n value is 0.013 times the hydraulic radius, okay, so the hydraulic radius for the half floor pipe is 0.5 to the power of 2 over 3 times the slope. Slope is 1%. So 0.01 1 over 2. And we can get the velocity is equal to 7.22 feet per second. So the travel time will be L divided by V, and the length is 2,200 feet divided by 7.22, and we convert the unit to hour, and we will get this is 0.085 hours. So the total concentration time is 0.219 plus 0.063 plus 0.085. This will give us 0.367 hours. And we need to determine the percentage of the time of concentration that is attributed to the overland flow. So the percentage of the overland flow is 0.219, the first term, that is attributed to the overland flow, divided by the total time of concentration, 0.367. This gives us 0.6, that is 60%. So this tells us the overland flow time has the greatest influence on the time of concentration, so it must be evaluated carefully. Okay, so let's look at next question. So in the problem 7.2.2, it shows that a comment is made in a paragraph which follows equation 7.14, suggesting the selection of the radius of the influence R node R0 can be somewhat arbitrary. And suppose the radius of influence for a 20 cm diameter well is approximately 250 meters, and we want to determine the percentage error in the discharge that results from this 20% different change in the radius of the influence. Okay, so basically we want to evaluate if we have small disturbance in this radius of the influence, how does that affect the discharge? Okay, so if I write down, it will be like if we have some variance in this radius of influence, how does that affect the discharge? Okay, so to answer that, we will use this equation shown on the screen here to evaluate the relationship between this R0 and Q. Okay, so let's do that. So because we want to evaluate plus or minus 20% change, that means we need to use 25 meter, that's plus 50 because it's plus or minus 50 for this 20%. So this will give us 300 and minus 50 give us 200 meter for the R node R0. This is the range we want to test. Okay, And let's write down the term for this equation. We will need to know H0, and this tells us it's a 50-meter thick unconfined aquifer. So H naught is 50. HW, because this is a drawdown, have the 3 meter. So HW is 50 minus 3 is equal to 47. Okay, so H naught is this, and we know the thickness of the unconfined aquifer, which is start from here. This thickness is 50. Okay, and a W, this drawdown here is 3, so we know this is 47. Okay, and what else do we need to know? Oh, RW. RW is the radius for this well, and we know the diameter is 20 centimeter, so that means the radius is 10 centimeter and is equal to 0.1 meter. Okay, now we have, one thing we also need to know is this conductivity K. And here you can obtain the K value from table 7.2, but here I will just give you the value. It's equal to 1 times 10 to the power of minus 3. Okay, so now we have all those information, we can apply the equation 7.14 to evaluate the change in the discharge. So we want to calculate discharge if the R0 is 300. Let's start with 200. So just follow this equation. Pi times 50 square minus 47 square divided by log R naught is 200, RW is 0.1, and we can get this is 0.12 cubic meter per second. Okay, this equation. And similarly, we can write for the Q300 pi times 1 times. This power just represent the same. The only change place is now the R naught is not 200 but 300. And we can get the answer is 0.114 cubic meter per second. So after we know that, we can calculate the percentage of the change. So we can somehow approximate. I mean, you can calculate that, but I will just use a really simple approximation for this. 4/2, that is 117. So the percentage of the change is 1 divided by 2 times the difference between 0.114 0.12 minus 0.114. That is the difference between these two, and we divide by this Q 250, 0.117, and these two is because we want to calculate this change. So we just divide this entire change into 2. Okay. So this gives us 0.026. This is 2.6%. So this actually tells us that the 20% change will result in plus and minus 2.6 2.6% change in the Q. This is unknown. Okay. So basically what you need is to use this equation 7.14 and calculate the discharge with different R0. Then you can estimate the corresponding changes in the discharge with different R node. So we can see that the influence is indeed quite small. Okay, let's look at the last problem for this week. We have a 40 centimeter diameter well, so this D is equal to 40 centimeter, that is 0.4 meter, and form this is 30.5 meter depth on confined aquifer at rate equal to 0.0151 cubic meter per second. And the drawdown observation away that we have an observation well, for example here, which is 50 meters away, and this drawdown is 1.5 meter, and the drawdown at the well itself, this part, is 6.5 meter. And we want to determine the radius of the influence of the well. Okay. Also, we need to determine the drawdown at a distance equal to 100 meter. So similarly, we will apply the equation 7.16 to calculate this. And because the K is not given in this problem, we will first utilize this observation, the drawdown on this observation well, and the drawdown at the well itself to calculate the K value. Okay, so H in this case is the distance here. Okay, here is H. So we can calculate that by 13.5 minus 6.5. That is 24 meter. And the observation part is here. So HOP. This is 30.5 minus 1.5. This is 29 meter. We have radius RB, ROB is 50 meter away. Here, this is ROB, and we have the radius of the well equal to 0.4 divided by 2, that's 0.2. So the only unknown in this equation is K. So we can plug in all those numbers. 24 square into 29 square minus the discharge is 0.0151 divided by pi times K log RB is 50 divided by 0.2. And we can solve the K. K is 0.0001 meter per second. Okay, so after that, we can apply this equation 7.16 again to solve R0. Maybe I can move this. No, I cannot move. Okay. So let me write down the equation here again. Okay. Okay. And now H will remain the same, but we want to calculate R naught, which assumed to be infinity. I mean, not infinity. I mean, we won't have any drawdown if we observe the radius of influence. So this HOP would be just the thickness of this unconfined aquifer. That is 30.5 square minus the same discharge value divided by pi times 10 to the, here is 10 to the power of minus 4 times the log ROB, which is R naught now, and R is still 0.2. Okay, so the radius of the influence is the only unknown in this equation now, so we can solve that. And this gives us that R naught, R0 is 318 meter. Okay, and we also need to calculate a drawdown distance at the 100 meter. So again, we can apply this equation one more time. So we have the same h, and now we want to solve at 100 meter. Okay, 24 squared. Now we want to solve h100 minus, this would be the same value, times the log. Our observed is at 100 meters, so this would be 100 divided by 0.2. So we can solve this h100. Will be 29.6 in this case. But we want to solve the drawdown. So the drawdown is 13.5, which is the thickness of the aquifer, minus 29.6. This gave us 0.9 meter. So if we visualize that, we have another observation well here. Okay, I know this is a really bad drawing, but I just need. The drawdown at this place is 0.9 meter. Distance is 100 meter. Okay, so for this last problem, you basically apply the same equation 3 times. The first time you can solve usually existed observation well. You can solve this k value. Then you applied it again. To solve this Arnold. After that, you can apply it one last time for solving the drawdown and this at an observation well that is 100 meter away from the well.